All right, so today we're going to be talking about increasing and decreasing functions. The definition for increasing and decreasing is as follows. So it says a function f is increasing if, and we're going to look at two x values. So x1 being less than x2, or in other words, x1 is smaller than x2, implies, and again this is for it to be increasing, implies that the y value associated with x1 has to be smaller than the y value associated with x2. So f of x1 is less than f of x2. And for the second one, if it is decreasing, that means that x1 is x1 being less than x2 implies that the y value of x1 is greater than the y value of x2. So here's some little pictures to kind of get your brain thinking about this, and you can draw them over here in the margin. So if this is x1 and x2, and this function is increasing, if we look here at this point here and this point here, this would be f of x1, and this would be f of x2. So you can see that x1 is in fact less than x2, and f of x1 is in fact less than f of x2. So that means that this is increasing. Alright, and vice versa in this graph down here. If x1 is less than x2, but it's decreasing, that means that f of x1 would be on top, or greater than, and f of x2 would be on bottom, or less than. Alright, and then we can kind of look at that also over here in terms of what it means. So if this is the graph of a function, we can look at it as increasing. Oops, that's not what I wanted to do. Increasing here, increasing over here, decreasing in the middle. And then here would be a relative maximum where f prime would equal 0. And down here we have a relative minimum where f prime equals 0. So this is kind of what we're going to be looking at today. So when a function is increasing, when a function is decreasing, relative mins, relative maxes, so on and so forth. Alright, so let's look down here at the bottom. Here's some tests for increasing and decreasing. If we look down here, we can scroll down. It says a test for increasing and decreasing. F must be continuous. There's that word continuous again. F must be continuous on a to b and differentiable on a to b. This first one, if f prime of x is greater than 0. So in other words, if f prime is positive for all x, then f is increasing on that interval. On the next one, if f prime of x is less than 0, then f is decreasing on that interval. And last but not least, if f prime of x is equal to 0, then f is constant on the interval. Or in other words, this is a horizontal line. Alright, so if the derivative is positive, it's increasing. If the derivative is negative, it's decreasing. And if the derivative is equal to 0, then it is constant. Then f is constant. So let's do our first example down here at the bottom. It says find the open intervals on which f of x is increasing or decreasing. So here's how I like to do this problem. Alright, the first thing we care about is these steps. There are only two steps to find increasing and decreasing, but I'll go ahead and write them down. Steps for finding increasing/decreasing. Number 1, find the critical points. Number 2, use a test number line or a table in order to figure out intervals of increasing, decreasing. So for critical points, I need to know where the derivative of this function is equal to 0 or where it's undefined. So I find the derivative of f of x. I get 4x cubed minus 6x squared. I have to find out where that equals 0. So if I factor out a 2x squared, I get 2x minus 3 equals 0, because I'm trying to find out where this equals 0. So I know that 2x squared will equal 0, or 2x minus 3 will equal 0. So x either equals 0 or x equals 3 halves. So those are my two critical points, x equals 0 and x equals 3 halves. So I found my critical points. The next piece is to create a number line, a test number line, or a table. And I kind of like to actually combine them into one. So I like to look at my number line here. So this is the point 0. And I like to put it above the number line. This is the point 3 halves. Put that above the number line. And I like to put a little box around those to know that those are kind of my breaking points. So either of those is either a minimum or a maximum because it's a critical point. Well, it technically actually doesn't have to be a minimum or a maximum, but it is a critical point. And then I like to choose numbers around that on the number line. So if I think of a number line in my head, if I have 0 here, anything to the left of 0 would be a negative number. So I'm just going to choose the easiest negative number I can think of. I'm going to choose -1. And then I need a number in between 0 and 3 halves, so maybe like 1 would work. And then I need a number to the right of 3 halves, so maybe 2. So those are my test number lines. So here's my test number line. From there I like to create a table. So I'm going to draw these two legs down. And then over here on this first row, I'm going to be determining whether or not f prime of x is positive or negative. And on the second row, I'm going to be determining what that means for f of x. So what does it mean for the original function based on what we find out about f of x? So what I'm going to be writing over here now is going to be things that you don't necessarily need to write out. You can just do them in your head. I'm just going to be writing them out so you guys can see where I'm coming up with what I'm coming up with. So what I'm going to do right now is I am going to take this -1 and in the derivative function, so I should actually probably write that derivative function back out. It was f prime of x equals 4x cubed minus 6x squared. So for this first one, I'm going to be taking this test value, -1, and I'm going to plug it into the derivative function to figure out if it's positive or negative. So that's what I'm doing right here. So f prime of -1 would be 4 times -1 cubed would be -1. Minus 6 times -1 squared would be 1, so that's -4 minus 6, which is -10, so that's a negative. So I'm just going to write, in red I'll write it so you guys can kind of tell the difference. I'm going to write negative. Alright, so that's the first one. My next test point, right here, my next test point is 1, so now I'm going to take 1 and plug it into the derivative. So f prime of 1 equals 4 times 1 cubed is 1 minus 6 times 1 squared is 1. So that's 4 minus 6, which is -2, which is also negative. So in this one, I'm going to write negative. All right, last but not least. I'm going to take the 2, my test value of 2, and I'm going to plug it in here. So I have f prime of 2 equals 4 times 2 cubed, that's 8, minus 6 times 2 squared, that's 4. So 4 times 8, that's 32, minus 24 is positive 8. So this is a positive. So now let's determine what that means for the original function. So for the derivative is negative in our test value over here of -1. So it's negative, and it's still negative in the second interval, and then it turns positive. So if you look back up at the top again, where it says test for increasing, decreasing, it said if the derivative is positive, then it's increasing. So this one is increasing. And it says for the number 2, if the derivative is negative, if it's less than 0, then it's decreasing. So these two over here must be decreasing. Now one brief thing I want to point out is this. Notice how I labeled this as f prime of x, and notice how I labeled this as f of x. The reason I did that is because it really helps on the AP test when people are grading your work if they can see exactly what you're talking about. So if you don't label those things, they might mark off a few points. So definitely label everything that you're talking about so it's very clear to them that you know what you're talking about. Alright, so we have our intervals of increasing, decreasing. Now we just have to actually write them out as a solution. So here's how we're going to write our answer. It says find the open intervals on which it is increasing or decreasing. So increasing, All right, this is the only this is the only interval right here where it's increasing. So it starts at 3/2, because that's my critical point. It starts at 3/2 and it goes to infinity. Then for decreasing, it starts at negative infinity, oops, and goes to 0, that's my first critical point, and then it decreases again from 0 to 3/2. And that is my answer. There's my interval that it's increasing, and there's my interval that it's decreasing. So it looks just like that. We're going to do a few more examples with this. Tomorrow's notes, by the way, have you do this, where you find intervals of increasing and decreasing, but then you go further and you decide what that means about the critical points, if they're maxes or minimums. So let's look at the next example. How many are there? There's 2, 3. Okay, good. This one's not that bad. Number 2. Number 2 says find the open intervals on which f of x equals cosine of x over 1 plus sine squared of x on this interval from 0 to 2 pi. So now we're not looking from negative infinity to positive infinity, but only from 0 to 2 pi. So step 1, if we look back at the previous example, step 1, find the critical points. So in order to find the critical points, we have to find the derivative. This derivative is a little bit lengthy because it has quotient rule and it has, quotient rule and it has a bunch of trigonometry stuff. So bear with me as we go through this. It is kind of lengthy. Do your best to follow along. If you need to pause the video at any moment in time, please do so. So let's see, quotient rule. I'm just going to go back to old school quotient rule stuff. So u equals v equals. So u is cosine of x, and v is 1 plus sine squared of x. So therefore u prime equals negative sine of x, and v prime equals, the derivative of 1 is 0. The derivative of sine squared of x is 2 sine of x, that's the derivative of the outside, times the derivative of the inside, so that would be cosine of x, because the derivative of sine is cosine. So when I multiply, here's my f prime of x. I multiply backwards first, so I get negative sine of x times 1 plus sine squared of x minus cosine of x times 2 sine squared, not sine squared, sorry, times 2 sine x cosine x, all over 1 plus sine squared x. So like I say, if you need a minute to comprehend that or a minute to kind of wrap your brain around that, please go ahead and do so now, so you can get that before we move on. So if I simplify that, let me write it a little bit smaller so we can fit all this on there. If I simplify that top part, I get negative sine of x minus sine cubed of x minus 2 sine x cosine squared x, all over 1 plus sine squared x. All right, in the top, I see sine, sine, sine. There's sine in all of them. So I'm going to factor out a negative sign. They're also all negative, so I don't want that negative there. So negative sine of x gets factored out, and let's see what gets left over. That leaves me with 1 plus sine squared of x minus 2 cosine squared of x, all over 1 plus sine squared of x. Like I said, it's a long problem. Bear with me. And keep pausing the video if you need to. All right, from here, there's one more thing we're going to do. So I'm going to erase some of this stuff up here, so if you don't have it down, just pause and write it down. All right, so I'm going to put it in red so you guys can kind of see where this is coming from. I'm going to use one of the trigonometric properties to replace sine squared, because I want each term to only have cosines or sines. Or each factor, I should say. So over here, I have sine of x, which is okay, because that's by itself. But in this factor, I have sines and cosines. So I want to get rid of that sign, because it's hard to solve problems that have more than one trigonometric function, I should say. So I'm going to use the property, the Pythagorean identity, that says cosine squared of x plus sine squared of x equals 1. Subtract cosine squared from both sides, so I get sine squared of x equals 1 minus cosine squared of x. And I'm going to use that to substitute that into here for sine squared of x. And I'm going to write it over here. So let me write this one more time. Equals negative sine of x times 1 plus, and instead of writing sine squared of x, I'm going to write what it equals, which is 1 minus cosine squared of x minus 2 cosine squared of x all over 1 plus sine squared x. Erase this down here. And last but not least, this is the last thing we're going to do to simplify. I can add my ones together and I can combine those cosine squareds. So I get negative sine of x times 2 minus, is that minus? Oh, this is supposed to be a plus here. 2 plus cosine squared of x. All over 1 plus sine squared x. Alright. That's a lot, I know. So if you need to ask me questions about that on Thursday, I can always help you. But make sure you have that written down. Try your best to understand it as it is. Sorry, this is supposed to be squared, so is this. Try your best to understand it as it is, but if you guys need help understanding it on Thursday, I am more than willing to kind of go back over this one with you guys. So all that was doing, all that we did there was find the derivative, because we were still looking for those critical points. So remember, the derivative tells us where the derivative is the derivative, but to find the critical points, we need to find out where the derivative is equal, either equal to 0 or undefined. So I'm first going to find out where the derivative is equal to 0. So the derivative is equal to 0 where the top is equal to 0. So there's two factors in the top. There's the negative sine of x, so we're going to find out where that equals 0. And there's also the 2 plus cosine squared of x. We're going to find out where that equals 0. We're also going to find out where the derivative is undefined, so where the bottom is equal to 0. And that is where 1 plus sine squared of x equals 0. So let's start with the negative sine of x. I divide by a negative, so I get sine of x equals 0. I'm trying to think where sine of x would equal 0 on the interval from 0 to 2 pi. And there, I'm trying to think, let's see if I can draw my little unit circle down here. Sine would equal 0 where y equals 0, so that would be here and here. So sine would equal 0. We won't count 0 because it's not included on the interval, but we will count pi. So at pi, actually we will count 0. 0, pi, and 2 pi. Now you're going to notice that we don't actually need to include 0 and 2 pi so much, but I'll talk about y in just a minute. Alright, for the 2 cosine squared of x equaling 0, I can subtract 2 over to the other side and take the square root. So I get cosine of x equals, when I subtract 2 I get negative 2, and when I take the square root I get that. But that's an imaginary number, so we don't need to worry about those. So yay, we get to kind of put a pin in that, and that one doesn't matter. Alright, and then we need to know where the bottom is undefined, so we subtract 1 over and we get sine squared of x equals negative 1, or sine of x equals the square root of negative 1, which is also an imaginary number. So we don't have to worry about these ones either. Alright, so we just eliminated a lot of our work, which is awesome. So we got critical points at 0, pi, and 2 pi. Now if you notice up at the top, it's an open interval from 0 to 2 pi, so we don't care too much about 0 and 2 pi, but we will use them as our boundaries so that we can kind of get an idea. So looking back at the first example, step 1. Step 1 was to figure out the critical points. We just did that. Step 2 was to do a test number line or a test table. So I'm going to go ahead and erase these. We have critical points at 0, pi, and 2 pi. If I erase all this, actually let me just clear the page. I can create my number line at 0, pi, and 2 pi. Oops, I like putting those on top. 0, pi, and 2 pi. Now the cool thing is we don't need any test points out here, and we don't need any test points out here because those are outside of our interval, because we're only looking from 0 to 2 pi, so I'm not even going to look at that. So I'm only going to look in between 0 and 2 pi. So I'm going to choose some easy numbers that are between 0 and pi, like for example pi over 2 is probably a good one. And then in between pi and 2 pi, maybe 3 pi over 2, because those ones are going to give me nice, good answers for cosine and sine. So the first thing I'm going to do is I'm going to evaluate f prime of x, the derivative, and determine whether or not it's positive or negative. The second thing I'm going to do is I'm going to evaluate f of x, using that information to determine if it's increasing or decreasing. So, pi over 2. Let's plug that into f prime of x, which I erased already, but I'll write it again right here for us. F prime of x equals sine of x, negative sine of x, times 2 plus cosine squared of x, all over 1 plus sine squared of x squared. Alright, so when I plug in pi over 2, sine of pi over 2 is equal to, I'll just write some notes over here. Sine of pi over 2 is equal to 1, so that's negative 1. 2 plus cosine of pi over 2 is equal to 0, so that's just 2 plus 0. Divided by 1 plus sine would be 1 plus 1 squared, which would be 4. So this would be negative 2 over 4, which is a negative number. So I'm just going to write negative. Alright, negative, perfect. For the second one, 3 pi over 2. If I plug in 3 pi over 2, let's see, sine would be negative 1, so that's a negative negative 1, times 2 plus cosine is still 0, over 1 plus negative 1 squared is positive 1 still, so 1 plus 1 squared. So that would be 2 over 4, which is positive. So to determine what that means for the original function, if it's negative, it's decreasing. If it's positive, it's increasing. So these are the intervals on which it is increasing and decreasing. So it's increasing from pi to 2 pi, and it's decreasing from 0 to pi. And all of that work for that answer. But it is going to help us later on in figuring out minimums and maximums, and it is going to help us later on in figuring out inflection points and everything. So make sure that you have that down. All right, last example of this one. So I'll go ahead and clear out of this. All right, this last one's pretty easy, and I like it because it is easy. It says use the graph f prime of x. So this is the graph of f prime of x. So use the graph of f prime of x given below to determine the intervals for which the graph is increasing and justify your answer. So if this is f prime of x, I'm looking for, remember that wherever f prime is positive, the original function was increasing, and where f prime is negative, the original function was decreasing. So if I can just use my highlighter really quick to highlight positives and negatives. I have a negative down here and a negative right here, and I have a positive right here and right here. So if I write those intervals, I have from 1 to 2 is increasing, and from, what is that, 1, 2, 3, 4 to 6 is increasing. And they want you to justify your answer. So when they say justify, you better write them a pretty good justification because they want to know exactly how you know that. So I'm going to write something, you can write something different, but I'm going to write something along the lines of saying, wherever the graph, sorry, this handwriting is so messy. Wherever the graph of f prime is positive, the original function f is increasing. So they just want to know something along those lines to make sure that you actually know why you're getting those intervals and not just kind of guessing. So make sure that you do that. Make sure you include a justification. All right, that's it for today. Go ahead and make sure you have all those notes. On Thursday when I come back, if you have any questions about any of those examples, especially number 2, I would love to help you understand them a little more.